Okay, the first speaker is Professor Nader Engheta from University of Pennsylvania. His talk is entitled Four-Dimensional Spatiotemporal Metamaterials. Nader doesn't need an introduction to this community. He's a past chair of Commission B. He received his PhD at Caltech. He's Nedville Ramsey Professor at the University of Pennsylvania. You can see that he has been with four different departments. Departments of Electrical and Systems Engineering, Bioengineering, Material Science and Engineering, Applied Physics, and Astronomy. So obviously his research interests span a wide range of areas. He received numerous and most prestigious awards from many different technical societies for his research. Among others, Balthasar Vanderpoel Gold Medal from URSI, IEEE Electromagnetics Award, Max Born Award from the Optical Society of America, Ellis Island Medal of Honor, Pioneer Award in Nanotechnology, and a gold medal from SPIE, IEEE Antennas and Propagation Society Distinguished Achievement Award. In fact, if I go through all of that, I'll cut into his speaking time. So I'm just going to say a few representative things from his biography. He's also a fellow of many different technical societies, IEEE, URSI, Optical Society of America, American Physical Society, Materials Research Society, SPIE, and American Association for Advancement of Science. And he has received many honorary doctoral degrees, So with no further ado, I would like to invite Professor Engheta to give his speech.
Thank you very much, Symbian, for your kind and generous introduction. May I share my screen right now? Let me see. Okay, very good. Thank you very much, Symbian. It's a pleasure and honor for me to be here today. I'd like to thank the USNC-URSI, in particular, Symbian, Mike, David, Gary, Kathy, and Anna, and all the members of the organizing committees of National Radio Science Meeting for the great efforts in putting this meeting together and for giving me a chance to be part of the event today. I'm very honored to have a chance to talk today. As you can see from the title of my talk, I'd like to give an overview of the topic of four-dimensional metamaterials. Well, what do I mean by four-dimensional metamaterials? We all know, by the way, that the functional materials have very interesting properties of wave interaction due to the spatial inhomogeneity of material parameters in 1D, 2D, and 3D dimensional in space. Well, why not bring the dimension of time also into the variation of material parameters? Now, the question is that why should we be interested in this? There are several reasons. One of them is the fact that by adding the temporal variations in addition to the spatial variation of the material parameters, or in place of the spatial variation of material parameters, we have more degrees of freedom and you can do interesting things with waves in these type of materials, as I'm going to present some of them in the talk today. But there were two other reasons and inspiration for me to get interested in this topic. One was the idea of time crystal that was introduced by Frank Wilczek in 2012. Nobel laureate Frank Wilczek proposed the idea that the same way that we have regular crystal, let me see how this works. Regular crystal, which is the spatial periodicity in the matter. Is it possible to have something that have a time crystal, he calls it, that will have a variation of that in time? This created a lot of interesting debate in 2012. And then a few years later, in 2017, two experimental groups of one, Michel Lukin from Harvard, and the other one, Chris Monroe from University of Maryland, experimentally indeed showed that it's possible to have time crystal, the idea of Frank Wilczek. Another inspiration comes from my friend, Professor Matthias Fink from Langevin Institute in Paris, that he showed how in the water wave, if you actually rapidly change, the acceleration by just, moving the water level, you can actually have very interesting time reversal properties that he can explore in order to find basically time reversal in forming the image on the surface of the water, as you can see from his paper in Nature Physics. So we got very interested in this topic to see how we can actually take some of these concepts into metamaterials and try to have an interesting possibility for wave-matter interaction. But as you all know, by the way, the time-dependent platforms in electromagnetics have a long history. In fact, the earliest paper I was able to find belongs to Morgenthaler in 1958, which showed that while you have a monochromatic electromagnetic wave in a medium, if you rapidly change the phase velocity of medium by changing the index of refraction of the medium rapidly, then some interesting features will come out of that. And then a few years later, we all remember Dr. Ron Fonte in our Commission B community, that indeed he's shown in 1971 some interesting properties of time-varying material. At that time, and of course, there are many other people at work on various aspects of time-dependent platform. But what we are interested is to see how we can actually take advantage of concept of metamaterial, combination also with the spatial aspect to have an interesting novel properties in wave interaction with materials. But before I show you what we have been doing, let me show you in the next several slides some of the basic and background concept of this temporal material concept. Now, we are all familiar with the simple Fresnel problem that we learn and we teach our students, in undergraduate course, that if you have a simple inhomogeneity, this is the simplest possible spatial inhomogeneity that we teach our students, that we have two media, two semi-infinite media, and the wave is coming like this, and we all teach students that that would give rise to reflection and refraction. But what is the dual of that in time? Imagine that you have an unbounded medium, and in this medium, there's a monochromatic wave is propagating. And then at the time t equal to t naught, you rapidly change the permittivity of the entire medium from one positive value to another positive value. What would happen to that wave while the wave is already there and you're changing the material? Now, this problem has been studied by several people in the past. For example, one of the important aspects is how to actually define the temporal boundary conditions. Now, again, we are all familiar with the spatial boundary condition between two media. This is the simplest possible problem. And of course, the guiding rule is, if we look at Maxwell's equation, we consider source-free Maxwell's equation, we have to make sure that the term with the spatial derivative would stay finite when you go across this sharp boundary between epsilon 1 and epsilon 2. And of course, that gave rise, to the very well-known boundary condition for E, H, B, and D that we teach our students for the source-free scenario. But what is the dual of that in the temporal boundary condition? In the temporal boundary condition also, you have to make sure that the term involving the time derivative stay finite. So if you have an unbounded medium and the wave is already in this medium and you rapidly change the permittivity from certain value to another value, what would happen to the temporal boundary condition in this scenario? And in that case, we have to make sure that vector D just before this change and just after this change would stay the same. The same thing for vector B, in order to make sure that the term with the time derivative would stay finite. Now that gives rise to this interesting boundary condition, which relates the value of permittivity just before the time and just after the time of change and the relevant electric field relation with that. Now, one thing I would like to point out as a side issue over here, that although we write D equal to epsilon E, we have to remember that this notion of D written as epsilon E is a notion in the frequency domain. If you are entirely in the time domain, of course, we all know that we have to write this in terms of a convolution because of the presence of the dispersion and the inertia of the material. And indeed, we have to take into account this kind of, intricate point of when you change the permittivity also in the medium as a function of time. Now, this is a topic that we are studying in my group, and we are showing that if the resonance of the material happens to be very far from the frequency of the wave that's already inside the material, you can approximately show that this relationship still stay true and hold true, and that's what we actually considering there. But actually, this dispersion has a very interesting properties on its own, which is not the subject of the talk today. And I'd be happy to talk to you offline in the discussion session later in the afternoon if you're interested. So Gove and Agrawal showed that if you have this type of changes in permittivity, what would happen to the relationship between frequency and wave number or wavelength? Again, if I would go to the standard Fresnel problem, we know that when the wave is coming and hit the standard spatial boundary between two semi-infinite medium, obviously the frequency of refracted wave is the same as the frequency of incident wave if the material is linear. But it turns out, by the way, that if you go into the temporal aspects of this, something else happens over here. If you have an unbounded medium and the monochromatic wave with the frequency omega-1 is already in this medium, and then you rapidly change the permittivity from epsilon-1 to epsilon-2, what actually remains conserved is the wave number. In other words, the wavelength would stay the same and wave number would stay the same, but as a result of change of the index of refraction, the frequency has to change. So it's a very interesting duality between the temporal variation of material property and spatial variation of material property that you see over here. So in one case, the frequency stay the same and the wavelength would be different from one material to other. In the other case, the wavelength would stay the same and the frequency has to change. This is something that in the plasma physics community known as photon accelerations that's been done there. Now, what is the consequence of this type of rapid variation of frequency? What we need to make sure is this relationship that you see in the bottom of the screen would stay conserved before the rapid change and after the rapid change of the permittivity, and also the same thing for permeability. Now, it turns out, by the way, if you do that, again, analogous to the Fresnel problem, in the temporal domain, you have something known as the coefficient for the forward wave and backward wave. So as you start with the monochromatic signal, as represented by this, complex exponential that you see over here, when you do this rapid variation, you split that wave into two parts. One of them would be forward going, the other one would be backward going. And by the way, you notice that in this formulation, K1 stay the same, because as I mentioned, that has to be conserved. But the frequency does change from omega-1 to omega-2. And Gove and Agrawal find, by the way, the expression for the so-called the magnitude of the backward wave and magnitude of the forward wave, the way that it's written over here. Now, this is kind of analogous, or the temporal analogous to the Fresnel coefficient that we have in the spatial boundary we have there. Now, let me show you, by the way, an interesting simulation just to give you a feel about the difference between spatial boundary and temporal boundary. In the left, you see a wave packet is coming, hitting a boundary between two standard medium. This is standard Fresnel reflection. You see the refracted wave has a shorter wavelength because epsilon-2 is larger than epsilon-1. But of course, the frequency is the same. However, if you do this in the temporal domain, you see something interesting. The wave packet is coming. You're going to start at the beginning of the simulation. And then rapidly, when you change the permittivity, you see two waves generated. One of them forward wave, the other one backward wave. And you notice, by the way, the speed of the wave will change, but the wavelength does not change. You see that actually the variation between the phases would stay the same, whereas, of course, you are changing the phase velocity of the medium. Okay, so these were the background materials that have been done, before in the community. So in my group, we have been interested to look at some of these properties of this temporal structure of the permittivity, in addition to or in place of the spatial one. And one of the things we decided to study is that how can we take advantage of electromagnetic parameters in the time concept over here. Now, we all know, by the way, that, of course, Maxwellian electrodynamics has a very interesting, duality and analogy between space and time. However, of course, there are major differences, of course, between space and time. In space, usually we have 3 dimensions that we deal in electromagnetics, but time has only 1 dimension. And also time, we have to be concerned with the causality of the time aspect, whereas in space, that's not the issue there. So we decided to see how we can actually take advantage of the parameter of electromagnetic to increase the degrees of freedom of time, and that's what we call it temporal anisotropy. Now, what do I mean by temporal anisotropy, an effect of that on antenna radiation? In the previous slide, I showed you what happened if you actually change the permittivity of the medium from one scalar value to another scalar value. But what if we actually change the permittivity rapidly from one scalar value to a tensorial value? In other words, to have it two different value of permittivity after the change, as opposed to one scalar case before. In other words, you're going from an isotropic material and you rapidly change that material into an anisotropic material. What would happen over here? Now, we all know that when we have isotropic material, of course, wave propagation in all direction will be the same. So the index of an ellipsoid becomes a spherical index. But one thing we have to make sure is that that temporal boundary condition still satisfies. So D1 should be equal to D2 just before the change of permittivity and just after that. But as a result, approximately we can write epsilon 1 E1 should be equal to epsilon 2 E2 with that condition that I mentioned with regard to the dispersion that I mentioned. But since here epsilon 2 is a tensor, whereas epsilon 1 was a scalar, not only the value of electric field will change, but also the orientation of the electric field will change, which means that you can actually change the direction of the energy flow and the Poynting vector midstream when you actually change that property there. So if you take a look at it, two interesting things can happen over here. One is you start with a medium that is isotropic. So in all direction, you have the same, index. Changing it to an anisotropic crystal in which in different direction, you have different index of refraction. But because wave number should stay the same in all direction, that means in different directions, the wave would experience different frequencies. This is actually quite an interesting property. In other words, you start with a wave that's going in different direction with the same frequency, but when you do this change of isotropic to rapid anisotropic variation in time, the wave in different direction would have different frequencies because it has to preserve the wavelength in that direction. Now, this is something that the Christoph Kallos has studied very nicely, and he calls it the concept of inverse prism. In other words, it's kind of like a rainbow effect. You start with a wave that's going in different direction with the same frequency, but when you do this rapid change, in different direction, you have a different frequency, kind of like a rainbow phenomena. This is what he calls the inverse prism, and he has studied this concept in this paper in 2018. But we decided to actually look at another properties of this thing, and that is what would happen to the antenna radiation, to a dipole radiation, if we have it in such medium. So imagine the following. Imagine that I have a medium, and I have an antenna embedded in this medium. And this medium is isotropic. Of course, we know the dipole antenna would radiate, normally the way we know. But then what would happen as the wave is already propagating from the antenna, you rapidly change the permittivity from a value to two different values depending on the component of the electric field in that medium. So let's say, for example, epsilon 2 XX is greater than epsilon 1, epsilon 2 YY less than epsilon 1. In the simulation in the left, I'm going to show you the interesting properties happens. First, I'm going to show you a two-dimensional dipole, like a line dipole that's oriented 45 degrees. And this, of course, would give rise to the standard, kind of like a donut shape radiation that we have. But this simulation is a 2D simulation. And you see this one is coming. And then right after this, you actually change the permittivity. And you see what happens. Even though originally the wave was going in the direction of 45 degrees, but you can actually midstream change the direction of the energy flow. So this will give rise to interesting property that I'm going to show you. We call it temporal aiming. You can actually move the energy flow of the beam by just rapidly changing the permittivity of the medium there. So originally the antenna is radiating in this 45 degrees direction, 135 degrees that you can see, but midstream when you change that, an antenna stops radiation for a moment just to show the effect. You notice what would happen, it goes to the left and right rather than the 45 degrees. And that depends on the relative value of these epsilon 2 XX and epsilon 2 YY. So here I'm going to actually flip the relation of the epsilon 2 XX with respect to this, and you see what happens. The same antenna that was propagating in the 45 degrees, depending on the relative value of the epsilon after the rapid change, you see what happens to the flow of the energy flow. So you can actually control the energy flow by just this rapidly changing, and that can have an interesting application in the integrated photonics area, where your radiator actually embedded in a material. And so that gets us to this concept of temporal aiming. And so the same way that we do beamforming, for example, in antenna array, here we wanted to see what we can do with regard to the wave packet by just changing the material parameters. So if we go back to the formula of the wave propagation in anisotropic medium, we all know that in anisotropic medium, the direction of the pointing vector is not in the same direction of the wave number. And the relationship between the original angle θ1, which is the direction of the wave number, versus the direction of the pointing vector follows this exact formula that we can find from anisotropic structure. So depending on the angle of the wave, how much the angle of pointing vector can change with respect to this depends on how value of epsilon2 with xx and zz will change. So this plot is show you how you can actually change the direction of the pointing vector with respect to the direction of the wave number when you go from isotropic to anisotropic temporal variations. So you have an original plane wave that's going like this. The color shows the direction of phase flow. The black arrows shows the direction of the pointing vector. But when you rapidly change that, you notice that, of course, you can do it like this. This is, of course, very well known in the crystal optics and photonics. But what we wanted to do is to see how we can actually do it in the form of antenna embedded in a substrate of the structure. First, let me show you a simulation for the Gaussian beam. If you have a Gaussian beam coming in this direction that you see there, and you rapidly change it in the midstream, you notice the Gaussian beam, rather than going in the original direction, is going to go sideways. It's going to go to the side, and there is a backward wave. And remember, in the formula I showed you, there is a little bit of backward wave. And actually, this backward wave is undesirable in many situations, but in some situations could be a good thing, which I will talk about in a few minutes. And if you, depending on the weight of the Gaussian beam, you can actually have this Gaussian beam goes more towards the side issue as you change this. Now, so essentially what we are saying is that you can control the wave packet, in this case Gaussian, and the energy flow of that, you can control it by just basically manipulating the material parameter in time. There is no spatial boundary over here. In other words, we are assuming the structure is unbounded over here. So you can actually use the temporal parameter in order to guide your wave. It's kind of like a temporal waveguide, if you will. And we said one of the interesting directions that we are pursuing is that can we do this in order to, particularly in integrated photonics, this become interesting, because if you have a source in your substrate and you would like this source to send your wave packet towards the receiver, again, embedded in the substrate that you have there, you can design this thing such that it gets to this point that you see there. But if you have several receivers, and depending on the demand, you would like to send that wave packet to the specific receiver without introducing a permanent spatial boundary, then you can use these temporal properties in order to basically midstream, basically usher or move the wave packet in the direction you want. So in the next slide, I'm going to show you an interesting simulation that we have done on this wave packet. On the left, you see what happens in the variation of the permittivity as a function of time from isotropic to anisotropic one as a function of time. And in the right, you're going to see what happens to this wave packet when it goes from the source towards either receiver 1 or receiver 2 or receiver 3 on demand in time without having any spatial boundary. So you will see what happens. This one come over here, you can change it and you can bring it back again. So in that case, you can basically move around this wave packet in the direction you want. You notice, by the way, that the wavelength does not change. The direction of the phase flow is not changing, but the direction of energy flow is changing over here. So I mentioned to you about that backward wave over here. So as we were studying this, something serendipitously we noticed, and that is it possible to have an equivalent of the temporal Brewster angle? Now, of course, we are all familiar with the Brewster angle for the parallel polarization between two dielectrics that we have there. At a certain angle, of course, reflection would be 0. It turns out that there is a temporal Brewster angle as well that we have found through our study over here. That is, if you have a wave propagating an unbounded medium and you rapidly change the permittivity, from isotropic to anisotropic scenario, is there any special angle that when you do that change, the backward wave disappears? And indeed there is. And in fact, if you look at the formula that we derived there and we make sure that under the certain condition, we would like to have a backward wave would be 0, then you get expression like this, which is basically become analogous expression for the Brewster's angle, but this would be entirely in the time aspect of that. And if you look at that structure I showed you for the Gaussian beam, remember this Gaussian beam comes in the angle 15 degrees. And when you do the rapid variation of permittivity, you see the backward wave. But if this Gaussian beam comes under the specific angle, which we call it temporal Brewster, then you don't see any backward wave coming from here. Now, so what other topic we can take this concept of time or temporal or four-dimensional with respect to the space? So we decided to look at the concept of scattering. Now, we're all familiar, of course, with scattering. When I say scattering, I mean conventional scattering, which in this case, I call it space scattering versus time scattering. And can we actually have something that we call it temporal lens? Can we actually use this concept in order to introduce the notion of temporal lens? So what do I mean by space scattering versus time scattering? What is a conventional scattering? In conventional scattering, we have an unbounded medium, let's say free space, and you have certain material, which is a permittivity as a function of x, y, z, okay? And you send your wave over here, let's say plane wave in this case, and you set the scattering. Now, the scattered wave, of course, has the same frequency of incident wave because the structure is linear, but the direction of the wave number or direction of basically momentum will be, of course, different in different direction and different amplitude and phase. What is the equivalent of that in the temporal materials? In other words, rather than having permittivity as a function of x, y, z, could we have a permittivity as a function of time? What kind of scattering we get there? Well, this is what actually Matthias Fink has done, as I mentioned, back in 2016. What he did is that he got a tank of water, and then he created a disturbance on this tank of water. As you can see from this needle, it creates disturbance. And while this wave is propagating on the surface of the water, he rapidly pushed the water up and down by putting a motor underneath of this tank. And because of that rapid change of the surface, you notice that actually he creates a backward wave and forward wave, and the original image actually is formed, kind of like a time reversal one. So we were inspired by this concept that Matthias did, and we decided to combine the two scattering together. So rather than having the entire structure changes with time, what would happen if we just change only a limited region of space with time? So imagine that you have an unbounded medium and you have a monochromatic wave is propagating. And then you come over here, you identify certain region of space, and then you try to change the permittivity of that region only, but not the rest, rapidly as a function of time. So basically, imagine something like this, that in this region, you start with the background and you rapidly change the permittivity and quickly bring it back. What happens to the wave, to the structure there? And you can actually keep doing this one, you know, kind of like with certain periodicity of rapid variation of this permittivity. Something interesting happens over here. And this is one of those cases that the backward wave becomes useful over here. So imagine that we have this and the wave coming like this, and you rapidly change that part and keep, you know, changing it, you know, periodically with this, you know, rectangular pulse that you see there. You notice that the original plane wave that was going over here is going to split into two. Some of them would be forward wave, some of them would be backward wave. But if you look at the backward wave, you notice it replicates the shape of the object. Now, why is that? Because as the original plane wave is going in the region that is all, you know, uniform, and then rapidly you change that permittivity at that point, at every point, essentially you're creating a dipole moment. And that dipole moment has the information of the magnitude and phase of that plane wave at that moment. So those essentially becomes a radiator, so to speak, becomes antennas themselves, and they start propagating both forward and backward. And because the phase and amplitude of those locations are preserved, the wave actually has the information about the structure. So basically it replicates the shape of the structure. can we take advantage of this to see what we can do with this backward wave? So imagine I have a slab, and this slab, it's the same value as epsilon outside, except at certain time, you're changing the permittivity of that back to some value and coming back. In that case, what happens? Everything in this slab, it creates that dipole moments of every place that has an information about magnitude and phase of that point. So as a result, the radiated wave would have information about phase and magnitude everywhere in that region. And you notice what happens when this thing's happening, the wave actually goes backward. Even though the incident wave was coming like this, but because of the time variation, you get a backward wave that essentially is going back towards the source. And that's what like a time reversal properties that we have over here. If we chose the size of this and this variation between these rectangular pulses properly, you can actually stitch together this backward wave and create something that resembles like a phase conjugation mirror there. So we decided to take advantage of this concept to see whether we can create something that we call it temporal lens. So imagine we have an unbounded medium, and imagine we specify certain region of this space that we would like to change its permittivity. So for a moment, there is no difference between this region and this region, it's the same material. But at certain time, we're going to change only this region, and let's see what happens. And we have a line source over here. Let me give you a line source over here. Now we don't have plane wave. This is just a cylindrical waves that's coming over here. And when the cylindrical waves gets in this region, we start changing the permittivity of this, periodically with certain period. What happens to the backward wave? This would be quite interesting. This is the simulation that you see, the total field that you see over here. But on the right of the screen, you see what happens to the backward wave. The backward wave from this so-called temporal lens is coming back and forming the location of the source that it was. So it's kind of like a phase conjugation structure, even though it happens entirely in the time domain over here. So by having this temporal lens, you can actually make the wave to actually go backward, basically tracing the phase that it used to have and creating the original source that it has there. Now, if this is indeed the case, can we take advantage of this in the scattering problem? Indeed, that's the case. By the way, this just shows the same picture, but it shows, the still picture of that as to what happens. It's just like being focusing over here, but this focusing happens because of the temporal variation of that region. Actually, in that region, the material is the same as before, except at only those moments that you are changing it. So you create this temporal lens. And in that case, we decided to see whether we can actually retrace the imaging in the presence of the scatterers. So we put a source over here, this bunch of scatterers that's over here, arbitrarily located. And this source starts to radiating monochromatic signal, scatters through all of this, eventually comes to this region. And when it comes to this region, you start, having these pulses that's going repeatedly there. And in that case, let's see what you get over here. This is the total field you get, but on the right, you're going to see the backward wave that's coming. So the backward wave is coming, retracing the phase, undoing the phase due to the scattering, and it's coming back and forming basically that hot spot that used to be the source there at that point. So, so this actually could have quite interesting possibilities for imitating the concept of phase conjugations, even though the structure doesn't have a nonlinear optical property. It's just the temporal variations that we have. Finally, we have looked at other interesting properties here, but in the interest of time, I'm going to give just one quick other example and move on to a different subject before the end of my talk. We actually also show that you can have a temporal coating, kind of like analogous to anti-reflection coating that we're all familiar with. This would be anti-reflection temporal coating. So instead of having a layer of material between two media in order to make the reflection zero, you can do that in time. In other words, you have a medium unbounded, and you want to change that medium from epsilon1 to epsilon2, which creates the backward wave. But in order to prevent that backward wave, you can go in two steps, very similar and analogous to the conventional anti-reflection, but this would be a temporal anti-reflection coating. And that actually can provide this interesting analogy. In fact, we derived this expression for the temporal quarter period, and you notice very interesting analogy. In the case of conventional spatial quarter wave, this layer should be lambda over 4. And of course, the relation between permittivity is a well-known relation, you know. In the case of temporal one, you notice the relationship of permittivity is the same, except here, instead of the thickness in space, you have period in time that has to change 1/4 of that aspect. There are other interesting property of non-reciprocity over here that in the interest of time, I can go into that, but I'd be happy to talk to you in the afternoon discussion sessions. And so this shows the simulation that we have in this structure. Okay. So that was one of the concept of using this time into material in order to create more degrees of freedom to do interesting things with it. But before I finish my talk, I'd like to talk about another way to increase degrees of freedom, and that is try to have a non-periodic metastructure in space. So for the remainder of my talk, material is not changing with time, but the structure of the material is very non-periodic. And one of the things we would like to do is to take advantage of non-periodicity in order to do information processing. Now, why are we interested in that? Because we would like to see whether metamaterial can be useful, you know, in artificial intelligence, machine learning, and eventually for neural networks. So this is a long-term goal we have. But as an intermediate goal, we ask ourselves this question: is it possible to use metamaterial in order to do information processing for us? And by information processing, I'm going to show you, we have shown and built the structure and did the experiment, which I will show you, that can actually does mathematical operation for us. In other words, we design materials that can solve integral equation for us. So what is the goal? So imagine you would like to design a material structure that consists of various elements with the proper size, proper shape, and proper material, and located in proper location, such that this structure would have a transfer function of your choice. Meaning that if you send an arbitrary signal into this structure and you look at the output of this signal, you would like the relationship between the output and this arbitrary input to be a specific transfer function you like to have, to be a specific mathematical operation you like to have. Now, we all know, by the way, that the convex lens, which is a standard lens in any imaging system, would do Fourier transforming for us. But that's actually a specific mathematical operation as Fourier transform. But what we are doing over here is that to open the possibility to any linear transformation to see whether we can design a material or new types of lenses that would do other form of transformation, not just a Fourier transform. Now, we have looked at the various different things. Again, I'm going to show you some examples before the end of my talk. So about 6 years ago, 6-7 years ago, we proposed the idea that how we can actually design a metamaterial such that it would do mathematical operation of your choice. For example, can we design a material that as you send a monochromatic wave with an arbitrary profile into the structure, by the time the wave comes out, obviously the profile would be different. And can we design this material that the profile of the output would be, for example, the spatial derivative of the arbitrary profile of the input? In other words, can we actually have a layered structure that would take the derivative in space for us, or would take the integral, or would take the convolution of that? And also any other linear operators that you do. One of the reasons we were interested at that time for this idea is that this could be an interesting possibility for image processing. For example, at that time, we designed this layered structure such that it would take the second derivative of the wave that's coming into it. By the way, when I say second derivative, I mean second derivative with respect to space of the profile of the wave that's coming. And the reason we were interested in that is because we all know that in image processing, the operation of Laplacian can take the edge detection. So if you're able to actually make the second derivative of any profile that's coming into this, is it possible to actually detect the edges of this? So in that theoretical proposal, and this is a result from our paper in 2014, indeed we showed that this is possible to have something that will actually pick up the edges. And indeed, this becomes an interesting possibility for image processing. Now, the current computers can do image processing, but they do it in the digital domain because you have to raster scan all the pixels and find the difference of the intensity of each pixel. Whereas in this idea, everything is analog and everything is done in parallel. So the entire image can go through the system at once. So the speed of this could be much faster. After this theoretical proposal, several groups actually followed this and experimentally showed that indeed it's possible to design metasurfaces that can take the derivative of the incoming signal there. So we were very excited about this possibility, and then we decided to put our goal is a more ambitious goal. So we asked ourselves this question, that now that we know how to design a metamaterial that can do mathematical operation of our choice, is it possible to design a material that can solve equation for us? So in order to do that, we decided to look at the most general linear integral equation known as the Fredholm integral equation of the second kind that you're all familiar with. So we wanted to see whether we can design a material can actually solve Fredholm integral equations for any arbitrary input for a given kernel. Now remember, specifically, I want to emphasize this point that this kernel is not translationally invariant. In other words, the argument is not y minus y prime, because otherwise that would have been convolution and you can do it before you transform. Intentionally, we wanted to make it hard in such a way that this would not be a convolution integration, which is not. So the idea was that now that we know how to design a kernel, the metamaterial that will give us this kernel, we need to create a feedback system over here that when you send an arbitrary input into this, when it goes through the structure, by the time it comes out, the output would be the solution G to this integral equation for any arbitrary input we want. We are pursuing two platforms of this. One of them is using inhomogeneous metamaterial, and that's the one I'm going to talk about for the next 5 minutes of my talk. And the other one also we are using by a concept of connection of Mach-Zehnder interferometers in photonics. David Miller at Stanford proposed the idea that if you have a combination of Mach-Zehnder interferometer, you can actually create a linear operator. So we were inspired by this concept to see what would happen if we introduce feedback there. Today, I won't have time to talk about the right platform. Again, I'd be more than happy to talk to you later in the discussion in the afternoon. So let's talk about the left one, and that will bring me to the end of my talk. So the idea is this, that if you give me an integral equation for a kernel, we can go ahead and design this inhomogeneous permittivity over here such that it will give us this linear integral operator for any arbitrary function g. And then you create this feedback system over here with the directional couplers that you bring your input over here. And then this input will get into the system after, being in the monochromatic system. Then you can look at the expression of the function over here, and that should be the solution to your integral equations. We did a lot of studies on this, and then we eventually decided to actually do the experiment on this. And in the experiment, we decided to choose this kernel. And this kernel does not represent any physical phenomena. This kernel is just a mathematical kernel. It is complex, as you can see. It is not separable. In other words, you cannot write it in terms of multiplication of one function of y, another function of y prime. And it is translationally variant. In other words, it's not function of y minus y prime. We use the concept of inverse design, which is optimization technique, to find out what is the distribution of the field over here. And here you can see that it kind of consists of two materials. One of them, dielectric, we decided for our experiment to use, Rexolite, which is the polystyrene, known material in microwave. And the yellow region is the air region. And indeed, it looks like you start with the dielectric and you create holes in it. That's what we call it Swiss cheese in my group. And it's very important to notice that the shape of this is obtained from the inverse design, and it's very non-periodic. And indeed, that would give you good degrees of freedom. And then we did a series of simulations on this to show that indeed it's working based on our theory. And then we build it. This is the rendition of the design. And we build this structure. And this is a photograph of the structure we have. You notice 5 waveguides, and you have basically 10 connectors for the coaxial cables. 5 of them would bring the input signal in with the proper amplitude and phase with the arbitrary input. And then what you read from magnitude and phase of the output, that would be solution to your integral equation. So let me show you the experimental results. Here, we excited one of the ports with the amplitude 1 and phase 0, and the other ports non-excited. And then you see over here 3 pairs of curves that you see over here. Theory 1, real and imaginary part, simulation of the structure that we designed, theory, real and imaginary part, and experimental result is the thick curve, real and imaginary part. You notice that all the real parts agree very nicely, all the imaginary parts agree very nicely. And we looked at the other inputs of this. And indeed, for the other inputs, you get the different outputs. But in all of these cases, experimental result agreed very well with our theory and simulation. So indeed, this structure can solve this integral equation for any arbitrary input we have. Then we extended this to, we call it, parallel processing in order to do this. We ask ourselves this question: is it possible to actually design one single Swiss cheese that can solve more than one integral equation at the same time, simultaneously? Take advantage of the fact that electromagnetic waves can go through each other without affecting each other. Indeed, that's what the case. We looked at this idea. In this case, we had to design a structure that would do 2 things at the same time. When you operated with the frequency omega-1, this should represent kernel K1. But when you operated with the frequency omega-2, the same structure will give you kernel K2. So we chose 2 kernels, as you can see in the bottom of the screen, and we designed this structure and we built it and we tested it, and indeed works very nicely. So in this one, when you operated with the 4 gigahertz, you notice that for these different inputs, the experiment, theory, and simulation agrees quite well. So it does actually solve for any arbitrary input for equation 1. But if you operate the same structure with the 5 gigahertz, you're going to get different kernel and different integral equations with the arbitrary input as well. So we are extending this into other direction. We are bringing this into the concept of silicon photonics in collaboration with my colleague Firuz Aflatuni. We have designed a similar Swiss cheese for the silicon photonics. This is about 30 micron by about 13 microns. And the chip has been ready, is being tested in the lab of my colleague, Professor Firuz Aflatuni. We are excited and eager to see what the experimental result will look like. We are very excited about this. Together with Professor Polman and Professor Andrea Alou, we are looking at the open aspect of this. In other words, can we do this with the open boundary rather than in the waveguide? This is also going quite nicely in the nice direction. Together with Professor Ahmed Hourfar and with one of my postdoc, Dimitrios Zorakis, and one of my students, Vahid Nikha, we are looking and extending this metamaterial machine for inverse scattering problem in order to see whether from the detected signal, we can actually predict what happens to the dipole moments or polarization moments in these scatterers. And we are looking also at the concept of incoherent signal. Up to now, whatever we're talking about is required phase, but it also can be extended to the intensity only. And also we are bringing nonlinearity into this as well. The reason we would like to bring nonlinearity is because it's important to bring this one to see whether we can extend this to solving nonlinear equation with waves. This is my final slides, is that indeed we have this vision that these type of nanomaterials can be useful to have basically analog computing in the micron scale. And imagine that you would actually do a 3D printing of this in the future, kind of like a rewritable CDs that we used to have, and to see whether we can actually in the future to write our own analog computer in the micron size, and you do the integral equation solving, and after that you can erase it and write another one instead. So I would like to thank those members of my group who have contributed directly and significantly to the work that I presented today. I'm very proud of them. And I'm very thankful to all of them. And I would like to thank the funding agencies for providing resources for us. And indeed, I showed in this 45 minutes that the four-dimensional spatiotemporal metamaterial can provide an interesting platform for wave-matter interaction with interesting functionalities. Thank you all very much, and I'd be happy to answer questions now and also at the 3:30 Mountain Time later this afternoon. Thank you.
Thank you for a fascinating talk, Nader. Are there any questions for Professor Engheta?
I would like to ask one, if it's possible.
Sure.
Go ahead.
Thank you, Nader, for a fantastic presentation. I just wanted a clarification. When at the beginning you were talking about a wave that enters a medium that is not bounded, and all of a sudden you change the epsilon of the material.
Mm-hmm.
My question is, so to change the material properties, I was wondering, you probably need to create another wave within the material, which is separated from the wave that carries the signal. I wonder intuitively how the timings of those two events are related to each other.
Okay. Thank you very much for the question, Danilo. Very good question. So here is the time aspect of that. When the wave is already in the material and you would like to change the permittivity, so the question is how fast you should change the permittivity. That's one aspect of this. And second thing, how do you change the permittivity? Now, I said rapidly, obviously nothing is ever instantaneous, because in order to change something instantaneous, you need infinite energy. So definitely is not instantaneous. But it should be fast enough that while you are changing the permittivity, the wave is already in the medium. That's actually an important aspect of that. That's one of the reasons right now we are looking at the ring resonator case, because there, the wave is already there. In that case, the rapid variation is not necessarily needed in that part. But to the second part of the question is that how do you change that? Now, that could be done differently. If you're, for example, let's say in the microwave system, if you have a two-dimensional transmission line, you can think about that you can actually change the capacitors of this transmission line, with the switches. And the switching of that can be done on top of the waves that's already there. If you want to do it, more in the higher frequency, then you can think about something like a liquid crystal concept that you can actually change that. That requires a stimulus there too. In other words, you need to have some additional energy in order to change the material properties. And also, if you want to do it in the nonlinear optics, that's a whole different thing that you can do with a laser signal. But let's talk about this more, because there are other interesting aspects of this that I'd be happy to talk to you if you're interested.
Sure. Thank you very much.
Sure.